When installing a 1000 amp 3-phase service with a generator disconnect and using 3-inch conduits with 4 parallel 400 American wire gauge conductors for phases A, B, C and neutral, the question arises about the appropriate size and installation of the grounding electrode conductor. The National Electrical Code, or NEC, provides guidance on this matter through tables 250.122 and 250.66. The critical aspect to understand is how these tables apply to your specific installation scenario. Table 250.122 dictates the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device in the circuit. In this case, with a 1000 amp service, Table 250.122 indicates that a 2/0 grounding electrode conductor is required. This table is primarily used to size the equipment grounding conductor, which is responsible for carrying fault current back to the source to facilitate the operation of the overcurrent protective device. Now, regarding the installation of the 2/0 grounding electrode conductor, the primary consideration is whether it needs to be installed in each of the conduits or a single conduit. The key here is to correctly interpret the application of NEC Table 250.66. This table is used to determine the size of the grounding electrode conductor where it connects to grounding electrodes such as ground rods, ground rings, or metal water pipes. Crucially, Table 250.66 applies when the grounding electrode conductor is run separately to the grounding electrode, not when it's run within the same raceway as the phase conductors. In your situation, since you are installing the grounding electrode conductor in one of the conduits that also contains the phase conductors, you do not need to refer to Table 250.66 for increasing the size of the grounding electrode conductor. You must install the 2/0 grounding electrode conductor in one of the conduits. It is important to ensure that the conduit you choose for the grounding electrode conductor is properly bonded to the service equipment. Proper bonding ensures that there is a low impedance path for fault current, which is essential for safety. The NEC requires that all metal enclosures containing electrical conductors must be properly bonded. This includes the service equipment enclosure, the generator disconnect enclosure, and the conduits themselves. Bonding is typically achieved by using bonding bushings and bonding jumpers. These devices create a secure electrical connection between the metal enclosures and the grounding system. Additionally, it's important to consider the requirements for bonding at the generator disconnect. The generator disconnect is a critical component of the system, as it allows you to isolate the generator from the service equipment during normal operation. When the generator is in operation, it becomes the source of power, and the grounding system must be properly configured to ensure safety. Typically, the generator will have its own grounding electrode system, which is connected to the generator frame. The generator grounding electrode system must be bonded to the service equipment grounding system. This bonding connection ensures that there is a common ground reference between the generator and the service equipment. The size of the bonding conductor between the generator grounding electrode system and the service equipment grounding system is typically determined by NEC Table 250.66 based on the size of the generator conductors. However, in your case, since you are running the grounding electrode conductor in the same conduit as the phase conductors, you do not need to increase the size of the bonding conductor. You can simply use the 2/0 grounding electrode conductor that you are already installing. When making connections to the grounding electrode system, it is important to use approved connectors and methods. The NEC specifies the types of connectors that are permitted for use in grounding applications. These connectors are designed to provide a secure and reliable electrical connection that will not loosen or corrode over time. It is also important to follow the manufacturer's instructions when installing grounding connectors. Improperly installed connectors can compromise the integrity of the grounding system and create a safety hazard. In addition to the grounding electrode conductor, you must also install an equipment grounding conductor in each of the conduits. The equipment grounding conductor is responsible for carrying fault current back to the source to facilitate the operation of the overcurrent protective device. The size of the equipment grounding conductor is determined by NEC Table 250.122 based on the size of the overcurrent protective device in the circuit. In your case, with a 1000 amp service, Table 250.122 indicates that a 2/0 equipment grounding conductor is required. You must install a 2/0 equipment grounding conductor in each of the conduits. The equipment grounding conductor must be connected to the service equipment enclosure, the generator disconnect enclosure, and all other metal enclosures that contain electrical conductors. The equipment grounding conductor must also be connected to the grounding electrode system. This connection ensures that there is a low impedance path for fault current. When installing the equipment grounding conductor, it is important to follow the same guidelines as for the grounding electrode conductor. Use approved connectors and methods, and follow the manufacturer's instructions. Improperly installed equipment grounding conductors can compromise the safety of the electrical system. Another important consideration when installing a 1000 amp service is the selection of the overcurrent protective devices. The overcurrent protective devices are responsible for protecting the electrical system from overloads and short circuits. The NEC specifies the types of overcurrent protective devices that are permitted for use in different applications. In a 1000 amp service, you will typically use circuit breakers or fuses as the overcurrent protective devices. Circuit breakers are automatic devices that trip open when they detect an overload or short circuit. Fuses are one-time devices that melt and interrupt the circuit when they detect an overload or short circuit. The size of the overcurrent protective devices must be selected based on the ampacity of the conductors that they are protecting. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The NEC specifies the ampacity of different types of conductors based on their size, insulation type, and installation conditions. In your case, with 4 parallel 400 American wire gauge conductors per phase, you must calculate the ampacity of the parallel conductors and select the overcurrent protective devices accordingly. The NEC allows you to increase the ampacity of parallel conductors by a certain percentage depending on the number of conductors that are installed in parallel. However, it is important to follow the NEC guidelines to ensure that the conductors are not overloaded. Once you have selected the overcurrent protective devices, you must install them in a suitable enclosure. The enclosure must be rated for the voltage and current of the circuit, and it must provide adequate protection from the environment. The NEC specifies the types of enclosures that are permitted for use in different applications. In a 1000 amp service, you will typically use a large metal enclosure to house the overcurrent protective devices. The enclosure must be properly grounded and bonded to ensure safety. In summary, when installing a 1000 amp 3-phase service with a generator disconnect and using 3-inch conduits with 4 parallel 400 American wire gauge conductors for phases A, B, C, and neutral, you must install a 2/0 grounding electrode conductor in one of the conduits based on NEC Table 250.122. You do not need to refer to Table 250.66 for increasing the size of the grounding electrode conductor, as you are installing it in the same conduit as the phase conductors. You must also install a 2/0 equipment grounding conductor in each of the conduits based on NEC Table 250.122. Ensure proper bonding of all metal enclosures and follow the NEC guidelines for selecting and installing overcurrent protective devices. Always consult with a qualified electrical engineer or inspector to ensure that your installation complies with all applicable codes and regulations. This ensures the safety and reliability of the electrical system. Remember that electrical work can be dangerous, and it is always best to leave it to qualified professionals. If you are not comfortable working with electricity, do not attempt to install a 1000 amp service yourself. Hire a licensed electrician to do the work for you. A licensed electrician will have the knowledge and experience to install the service safely and correctly. They will also be familiar with the NEC and other applicable codes and regulations. By hiring a licensed electrician, you can ensure that your electrical system is safe and reliable. Always prioritize safety when working with electricity. Electricity can be deadly if not handled properly. Follow all safety precautions and use the proper equipment Wear appropriate personal protective equipment such as safety glasses, gloves, and a hard hat. Never work on live electrical circuits. Always turn off the power before working on any electrical equipment. If you are not sure how to do something safely, ask for help. There are many resources available to help you learn about electrical safety. You can take classes, read books, or watch videos. You can also contact your local electrical inspector for advice. By taking the time to learn about electrical safety, you can protect yourself and your family from harm. In conclusion, properly sizing and installing the grounding electrode conductor and equipment grounding conductors is crucial for the safety and reliability of a 1000 amp electrical service. Understanding the application of NEC tables 250.122 and 250.66 is essential for ensuring compliance with electrical codes and regulations. Always prioritize safety and consult with qualified professionals when working with electricity. Finally, after installing the grounding electrode conductor, visually inspect all connections to ensure they are tight and secure. Use a torque wrench to tighten connections to the manufacturer's specifications. This helps prevent loose connections, which can cause overheating and electrical hazards. Document your work by taking photos or videos of the installation. This documentation can be helpful for future maintenance or troubleshooting. Keep a record of all materials used, including the size and type of conductors, connectors, and enclosures. This information can be useful for future reference. Obtain the necessary permits and inspections from your local electrical inspector. The inspector will verify that your installation complies with all applicable codes and regulations. This helps ensure the safety and reliability of your electrical system. After the inspection, address any deficiencies that are identified by the inspector. This ensures that your installation meets all code requirements. By following these steps, you can ensure that your 1000 amp service is installed safely and correctly. Remember that electrical work can be dangerous, and it is always best to leave it to qualified professionals. If you are not comfortable working with electricity, do not attempt to install the service yourself. Hire a licensed electrician to do the work for you. Also, it is good practice to label all components of the grounding system, including the grounding electrode conductor, equipment grounding conductors, and grounding electrodes. Use permanent labels that are resistant to weathering and corrosion. The label should clearly identify the function of each component and its connection point. This helps facilitate future maintenance and troubleshooting. Consider using a ground fault monitoring system to continuously monitor the integrity of the grounding system. A ground fault monitoring system can detect ground faults early, before they can cause damage or injury. The system can also provide valuable information about the location and nature of the ground fault. Ground fault monitoring systems are particularly useful in critical applications such as hospitals, data centers, and industrial facilities. When installing the grounding electrode conductor, avoid sharp bends or kinks in the conductor. Sharp bends can increase the impedance of the conductor and reduce its effectiveness. Follow the manufacturer's recommendations for the minimum bending radius of the conductor. Support the grounding electrode conductor properly to prevent it from sagging or coming into contact with other objects. Use approved cable ties or clamps to support the conductor. Ensure that the supports are spaced appropriately to prevent excessive sagging. When making connections to grounding electrodes, such as ground rods or ground plates, ensure that the connections are made below grade. This helps protect the connections from corrosion and physical damage. Use approved grounding clamps or connectors that are specifically designed for direct burial applications. Backfilling the trench with clean soil that is free of rocks and debris. This helps protect the grounding electrode conductor from physical damage. Compacting the soil properly to ensure that the conductor is properly supported. This also helps prevent the soil from settling, which can damage the connections. If the soil is corrosive, consider using a corrosion-resistant coating on the grounding electrode conductor. This can help extend the lifespan of the conductor and prevent it from corroding. Regularly inspect the grounding electrode system to ensure that it is in good condition. Look for signs of corrosion, damage, or loose connections. Repair any deficiencies promptly to maintain the integrity of the grounding system. Keep a record of all inspections and repairs. This documentation can be helpful for future maintenance or troubleshooting. Consider using a surge protective device to protect your electrical equipment from voltage surges. Voltage surges can damage or destroy sensitive electronic equipment. Surge protective devices divert voltage surges away from the equipment, protecting it from damage. Surge protective devices should be installed at the service entrance and at any sensitive electronic equipment. Finally, always remember that the grounding system is a critical component of the electrical system. It is essential for protecting people and property from electrical hazards. By following these guidelines, you can ensure that your grounding system is installed safely and correctly. And remember, working with electricity can be dangerous. If you're not comfortable working with electricity, do not attempt to install the service yourself. Hire a licensed electrician to do the work for you. By hiring a licensed electrician, you can be sure that the work will be done safely and correctly.